Our discussion today will be about voltage. Voltage is one of four, if you will, concepts that are important. If we say, for instance, power, we say resistance, we say current, and voltage would be the fourth one. So with that being stated, we will continue on with our discussion, God willing. So voltage, what is voltage? So voltage is EMF expressed in volts. So basically, it is a way to express the value of EMF. For instance, you say the EMF is 120 volts or 120 volts, or the voltage is 120 volts. All three of these ways is a way which pretty much expresses the same exact thing. So all of these express what is called EMF. EMF is electromotive force. So as we can see, E stands for the electro, M stands for the motive, and F stands for force. One thing which is also important is that voltage does not flow. Rather, it causes other than it to flow. EMF is similar to, if you will, pressure, which is in a water line or in a hydraulic circuit, for instance. It is similar to the force that will push, if you will, the water or the fluid through the line. So with that similarity, EMF is similar in the regard that it is pressure, which would force, if you will, current through an electrical conductor. As was stated, it basically, and we can refer to EMF as, if you will, we express it as voltage. So we express the amount of EMF in terms of volts or voltage. Measuring EMF. So you measure EMF or voltage. For instance, we'll say voltage. So you measure voltage by selecting 2 points. So basically, this terminology by selecting 2 points is very crucial. So by that, we will explain what we mean by points. So in another way, supposing that we have a winding, and we will call this point A, and we will call this one point B. So voltage is measured between both of these points. So this is what you would measure some voltage. Volts, for instance, we'll say volts. And whatever the difference is between these 2 points is going to be the voltage. So by that being said, in other ways, we can actually say that voltage is a difference between 2 points. That is a difference of potential between 2 points in a circuit. And the instrument which is used to measure volts is a voltmeter or a multimeter for example. We will now move on with discussing the types of voltage. So in alternating current, we have several types of voltage, or in AC systems, we have several types of voltage. So because we consider alternating current, it alternates. So we have RMS, we have instantaneous, we have maximum, we have peak to peak, and we have average. Our RMS is the root mean square. Or, if you will, this is pretty much the value which is equivalent to DC voltage. It is the equivalent to steady state DC voltage. So that means that a RMS voltage of 120 volts is equivalent to 120 volts DC. Instantaneous voltage is the voltage at an instant. So with that being said, if we refer to our sine wave of voltage, we know that we can pick off at certain instances with regards to time. So this is going to be our x-axis. This will represent our instances. So our instances usually in electrical are in electrical degrees. So we have 0, we have 180 degrees, and we have 360 degrees. The instantaneous voltage is the voltage value at some point along this sine wave. So you could find the instantaneous value at 180, which is going to be 0 volts. You can find it at 0, which is going to be 0. You could find it at 90 degrees. Which will basically be the maximum value. So at 90 degrees, it will be the maximum voltage. That leads us to maximum voltage. So maximum voltage is the maximum between here and here. So between this point, that is the 0, up to this point here is going to be the maximum voltage. We will call it EM. So EM is E maximum. Instantaneous voltage is, we can basically represent that, if you will. We will represent it as EI. Peak to peak voltage is basically the voltage from this point to this point. So this is considered a peak, and this is considered a peak. So peak to peak voltage would be the voltage from here to here. So if you were to measure peak to peak voltage, that being that if this, for instance, say that it is 100 volts, and this was 100 volts, the peak to peak voltage would be 200 volts, because peak to peak voltage is basically twice the maximum voltage. So therefore we have that E, so we have peak to peak voltage equals EM times 2, or twice the E maximum. That would be the peak to peak, or the peak voltage, if you will, twice the peak voltage. The average voltage is the basically the average. So it is the average amount of voltage, which is averaging the different instances that will happen along this line, or if you will, along this sine. On this side, we're going to pick a positive alternation. So it is the average value of voltage that is between, that would be basically the average value that all of those numbers, for instance, you would add the different instantaneous voltages, and then you would determine the average. Usually that's by dividing it by the number of voltage measurements that you have. So that's generally how usually averages are done. However, this value, sometimes we can actually approximate it. So it's basically approximately 0.637 times the E maximum. So the maximum voltage. So it's approximately 0.637 the times the maximum voltage. So therefore the maximum voltage times 0.637. That would be the average voltage. So we get it here that now I will draw out I will label the different RMS, instantaneous, maximum, peak to peak, and average. So as we got our maximum voltage is from here to here. So that's clear. So that is that from here to here would represent our EM, or the Emax. So the RMS, starting up here, so we have our Emax is basically from here to here, so it's the full amplitude. The RMS is going to be less than amplitude. For instance, if this were to be 100 and if the Emax was 170 volts approximately, the RMS value would be 120. So that puts us, this is not to scale, but just say for instance that this will be the E RMS. The average voltage is pretty much just an average. It is an average. So let's just say, for instance, that we would just keep that at the average voltage being this value here, whatever that would be. So the EM, so say for instance you have 120 multiplied by, for instance, it's about 120 multiplied by 0.637. Now, as far as the instantaneous voltage, as we know on any of these instances, such as at 90 degrees, that would be the instantaneous voltage. So supposing that we wanted to find the instantaneous voltage at 90 degrees, it would basically be the full value. If the value of this were to be 100 volts, then it would equal the EM. So the instantaneous voltage, the voltage at the instant of 90 degrees, will equal the EM voltage. Now, if it were to have been found at some other degrees, for instance, if this be 100 volts, and you wanted to find it at an instant of, for instance, for example, let's just take, for example, 180 degrees, as we mentioned previously, it would be 0. It would be 0. So, with that being said, instantaneous voltage is represented by an equation. So that would be that instantaneous voltage is equal to the EM, so the E maximum, what we have here, E maximum multiplied by sine theta. Sine theta. So with that being said, we have it that the EM is where EM is basically the E maximum, and the sine theta is basically the location, the sine of the angle that you would wish to find the value of voltage at that instant. We will eventually go more into this as the video proceeds, but for now this is pretty much enough at this point. Now, as far as the voltage, which is the common voltage, that would be the RMS voltage. So anytime voltage is mentioned, the terminology of voltage is mentioned, it is going to refer to the root mean square value, or the RMS value. Yes, it may be that someone could be referring to instantaneous, maximum, peak to peak, average, or some other type of voltage. You have, for instance, forward voltage, you have reverse voltage, for instance, you have all kinds of different types of voltages, descriptions of voltages, and voltages which describe certain things. You have for instance, breakdown voltages, things of that nature. But for this situation, we are going to be talking about voltage, and the meaning of our voltage is that it is going to be RMS voltage. Now that we have discussed the types of voltages, we will continue on forward with speaking about the usage of voltage in the NEC and throughout the trade. So some of the terminologies that we use to describe voltage is, for instance, we say, for example, line to neutral, or line to line, or line to ground, or hot to neutral, or hot to ground, phase to ground, phase to neutral. All of these are basically ways that we express voltage, and we are describing the voltage that we are reading by, for instance, line to line, or L to L, or line to neutral, meaning that it would be line to neutral voltage, or line to ground voltage, or hot to neutral voltage, or hot to ground voltage. Similar to line voltage, or hot to hot voltage, or leg to leg voltage, or phase to phase voltage. Basically, all of these, let's say for instance, line to line, hot to hot, these voltages, phase to phase, these are basically, if you will, synonyms for line voltage. All of these are basically synonyms for phase voltage. So usually when we speak about line voltage in general, is basically line to line, or hot to hot, or leg to leg, or phase to phase. Phase voltage is L to N. Generally speaking, we say line to ground, for instance, or hot to neutral, or phase to neutral, or phase to ground. One thing that is important is that line to line, hot to hot, leg to leg, these voltages, or these descriptions for voltage, are used to also talk about phase voltage in some instances. One of those instances is in single phase systems. So that being said, these can also refer to voltages in single phase systems. So that is in single phase. That is that in three-phase systems, these refer to the line voltages, not phase voltage. But in single-phase systems, these do basically, when we say hot to hot, or leg to leg, or line to line, we are talking about phase voltage. However, this term phase to phase, that is not what is meant when we say that, when we are testing, for instance, a single phase system and between the lines. For instance, say that we have a single phase system. If we consider this A and we consider this B, when we test between these 2 points, as we discussed previously, is in here, what is being read? So that is that the voltage the volts that's being read is what? It is the phase voltage. As far as the NEC is concerned, the terminologies which are used is line to line, for instance, or phase, for instance, voltage, or sometimes what's mentioned is line voltage, for instance. But pretty much it is understood that these pretty much refer back to the discussion here, is that we are measuring a voltage. Now in the field, sometimes the terminologies are flipped. However, as we mentioned, line to line, we have line to neutral, line to ground, hot to hot. These are usually terms we say in the field. It's concise, if you will, hot to neutral, hot to ground. Usually in the power company's establishment, they like to say phase to ground, for instance, phase to ground voltage, or phase to phase voltage, or they might say phase to neutral voltage, for instance. We came down pretty much to our understanding that all of these terminologies refer to these either phase or line voltage. We will define what is phase voltage and what is line voltage in the coming here. It will be of our interest now to consider the differences between phase and line voltage. So line voltage is what is measured across two phases, and phase voltage is what is measured across a single phase. For example, as I mentioned, this is considered a single phase. We will use the same example. We have A and we have B. So this measurement will be considered phase voltage. Eventually, we will get into the particularities of this, for instance, but for now, this pretty much concludes what we mean when we say line and phase voltage. It will now be of our interest to discuss voltage, which we consider system voltage. So that is the voltage of a system. So system voltage is the voltage of a specified system. So these voltages, that is the voltage of a specified system, can actually be classified. We can divide them into two categories, that being nominal and actual. Nominal, that is nominal system voltage, or the system voltage which is considered nominal, is a hypothetical thing. That is that it is a value which may not necessarily be the case, but it is as conceptual. It is a concept. Conceptually, it is to be the voltage. The actual voltage is the real voltage. So when you say, for instance, for example, when you read between, in our example that we gave previously here, supposing that we read the voltage between here, these lines here, and it was 120 volts, for instance. That is basically the actual voltage which was measured and found to be the case. Now, this voltage may vary. It may actually vary. For instance, it could have been, for example, 123 volts. So if it was 123 volts, this is not considered usually a nominal system voltage. However, we would consider it to be the actual voltage. So the actual voltage varies within a reasonable range of the nominal voltage. So as we mentioned, the actual voltage is the real voltage. The nominal voltage is the hypothetical value. So for instance, 122.40 volts is a hypothetical value because it's the nominal system voltage. The actual or real voltage would be 123.246, generally speaking. Now, not that you could not have measured 120. It is a possibility you could have measured 122.40, just as you could have measured 123.246. However, this value, as we mentioned, it is a hypothetical value. And as far as the actual voltage, this is the voltage in which we measure in the field usually. The important thing to take here is that the nominal voltage is actually what is used to classify the system voltages. So this is used to classify system voltages. That is, this system's nominal voltage would be 122.40. For example, there are several types of nominal system voltages. There's 120, 240, 480, 277. There are other types of system voltages as well. We have, for instance, if we refer back to the NEC, we can see that it states, unless other voltages are specified, for purposes of calculating branch circuits and feeder loads, nominal system voltages of 120, 120, 240, 208, 120, 240, 347, 480, 277, 480, 600, 347, and 600 volts shall be used. So in the NEC, this is the voltage in which we use as far as our calculations are concerned. For the purposes of our calculations, it is the nominal system voltage. As far as the NEC's definition of the nominal voltage is a nominal value assigned to a circuit or system for the purpose of conveniently designating its voltage class. And it gives a few of the voltages, as we have mentioned, the 120, 240 volts, 480, 277, and so forth. An additional thing which is also important to realize is that there are other types of system voltages. They may be sort of, odd, if you will. However, the system voltages which are most commonly used, as we were mentioned, as was stated in the NEC, is 120, 240, 480, 277. You also have 208, 120. This could be 120, 240. It could be single phase. It could be 4-wire 3-phase. This is in reference to 3-phase. This is in reference to 3-phase. This can be single or 3. The important thing to note here is that in some situations, well, in many situations actually, when we denote a system, a system's voltage, we usually say, for instance, it would be 120, 240 volts, 3-wire, or for instance, single phase 3-wire. And you have sometimes, for instance, 120, 240 volts, 4-wire, 3-phase. In reality, usually when there is a 120, 240 3-wire system, it is a 3-wire system. As far as the 120, 240 4-wire system, it does not necessarily mean that there would have to be, the number of wires, for instance, could change. You could have 4 wires also here. You could have 5 wires here, for instance. The number of wires, it is important to know that the number of wires are not actually what determine what we consider phase. Neither does the number of wires. As you know, for example, we have 3, we have 4. It does not determine the number of phase. The number of wires is just, for example, as we mentioned here, for instance, a 120, 240 system. These are our 3 bars. For instance, we will consider this L1, we will consider this L2, we will consider this N. These are our 3 bars. So these are just, if you will, connection points along the phase. Now that we are in the discussion of systems, particularly alternating current systems, the systems themselves can be divided into single phase and polyphase. We cannot forget that our whole point of this discussion is actually the discussion on voltage. However, we have moved past system voltages. We mentioned that system voltages are either nominal or actual. From this discussion on, we are considering ourselves to be speaking about nominal voltages. And we also discussed that we have 12240, for instance. We have single phase, we have three phase. Now we are going to mention the different types of systems. As was mentioned, we have single and we have polyphase. A single phase system is a system which at any instant has but a single sine wave of voltage. A polyphase system is a system which at any instant has more than one sine wave of voltage. That basically means the following. This is an example of a single phase system. This is an example of a polyphase system. These are going to be voltages. So these are voltages. We see, as we discussed previously, that the voltage of an alternating current system is a sine wave. As we see, we did discuss in past that along the x-axis are going to be instances. These instances are usually expressed in in degrees. So we have 0 degrees, we have 180, and we have 360. These are usually expressed in degrees. So a single phase is defined as if you have a wave under consideration, a sine wave under consideration. You can clearly see that this is a sine wave, a single sine wave of voltage. If, for instance, in a single phase system, if there was a measurement across A and B, that is across this single phase, the equivalent would actually be a sine wave. That is, if there was an oscilloscope. If you had an oscilloscope which was connected across this, there would be graphically shown a single sine wave. That is that on our x-axis, this would be our y-axis. On our x-axis is going to be the instances. If we were to intersect this point, or let's say, for instance, at this instant of 90 degrees, there is only but this line only intersects through this graph of the sine, the sinusoidal wave. It only graphs. This graph is intersecting this graph only at a point, and there's only one sine wave that is being intersected by this line. If you were to go about any instance, for instance, if we were to go to 180, there's only but one. If we were to go to, this would be 270, there's only but one sine wave. And for the other instances, for example, let's say 30 degrees, maybe a bit about right there, there's only but one sine wave of voltage. That is the definition of a system which at any instance has a single sine wave of voltage. That's the definition of a single phase. A polyphase, or a polyphase system, is basically the opposite. So as we mentioned previously, we know that this is going to be our y-axis, and also our y-axis represents the amplitude. The x-axis we are only concerned with as of right now, because we are determining the points along at instances along the sine wave. So again, if we were to look at an instance of 90 degrees, and we were to construct this line, it intersects two sine waves. That is, it would intersect this sine wave and it would intersect this sine wave. For instance, we call this sine wave A and we call this sine wave B. it would intersect sine wave A and sine wave B. Now the values, the amplitude, for instance, in this situation of B is going to be 0. The amplitude of this one would be the maximum amplitude, as we discussed, because this is at 90 degrees with respect to the sine wave of A. At this instance, we see that there are two intersections of, there is an intersection of two different sine waves. Similar to this instance, there's also another intersection in which there are two sine waves of voltage. So that being said, by definition, this is considered a polyphase system. By definition, this is considered a single-phase system. A single-phase system, as was mentioned previously, is a system in which there is only but at one instant, at any instant, for instance, at any instance, there's only but one sine wave of voltage. Similar to the polyphase system, the concept is the same at any instance. How many waves, sine waves of voltage are at that instance. And in polyphase system, there could be 2, there could be 3, there could be 4, there could be 5, there could be 6. There could be more than one sine wave of voltage. Thus far, we have discussed that alternating current systems are divided into two types, single phase and polyphase. We will now move on to discuss what a single phase voltage is. The single phase voltage of the system, and a little more detail than what was mentioned at this point here. So as we mentioned previously, this is an example of a single phase, and this is an example of a polyphase system. So we have a single phase system and a polyphase system. A single phase voltage, if we were to represent or illustrate the generation of a single phase voltage, we can equate it to something similar to this. We have, if you will, a coil or a winding, and we have, for instance, our poles, north and south pole. Now, the actual construction of a generator, if you will, there's a more detail to it. However, this is enough, this is adequate, if you will, to explain the idea behind the what is a single phase voltage. So, with that being said, if we consider, as we mentioned previously, this would be our winding. This is a single phase. And we know that in order for a EMF to be generated, it is basically by the basic principle of there being a conductor, which is basically cutting a field, or it could be the other way around. But there has to be a movement, a relative movement between a field and a conductor. So, in this situation, let us consider these to be our poles. Well, would be our pole pieces. We just have a north and a south pole. This is a two-pole field. Now, we only have a single phase. We will consider the positive direction would be in this direction. So back to our diagram when we discussed about the single phase system. As we can see, when A rotates, we will call this 0 degrees. We'll call this 180. The rotation, so we have 0, we have 180, we have 90 degrees. And then we have 270 degrees. So the mechanical rotation of this phase, or winding if you will, the winding, when it's at 0 degrees, there will be no voltage. The instantaneous voltage, that is going to be at 0, is going to be 0. So if we refer back to when we were discussing voltages, types of voltages, we said in general, when we refer to voltage, we're referring to RMS. However, in this discussion, we are referring to the instantaneous voltage. This is an example of where instantaneous voltage is necessary to know. When this winding is at this position, that is A is going to be here, there will be 0 volts. As A moves and it begins to be at about 30 degrees, if you will, the voltage will be at this magnitude here. When the voltage, when this continues, we will just refer to this as the winding. When the winding continues on and it reaches 90 degrees, the voltage will be at this instance, so it'll be at maximum. So we have at the instance of 90 degrees, as we mentioned previously, is going to be the maximum voltage. So that means it will be in a positive direction. So this is the maximum positive direction. This would be the negative direction. The voltage will be in the direction of, it will be positive for this situation. So when it is at 90 degrees, we will be at a positive voltage. When A continues through its cycle to 180 degrees, it begins to reverse to become less. It becomes less, and it approaches 0. At 180 degrees, it is going to be 0. That is when A rotates all the way here, and now it would be in this location. It would be considered 0 volts and 180 degrees. As A rotates, so we have A, let's say this is A continues on here, and as it approaches the South Pole, it is now going to be from 0 to its negative. It's going to have a negative sign, as we can see here. It would be negative. And then it will reach a negative maximum value at 270 degrees. And then as it continues on up to 0 degrees, it will reach up to this point. So from 270 and onwards, it is equivalent to this location here, and it goes back to 0 degrees. So this is basically the generation, the concept of the generation of a single phase. As for the generation of a polyphase voltage, it is similar in the aspect of the single phase voltage. So we have the same setup. We will consider these to be our pole pieces, north and south. We will consider this to be our positive direction. So the rotation of, it could be either the actual field or it could be the windings themselves. But in this situation, we're going to consider the windings to be in motion. And this is basically considered the armature. So basically, it would be rotated in a counterclockwise direction, which will generate what we call positive voltages. So with that being said, we still have the single phase as similar to what was here, we will label it A and A prime. We have another phase. So we have two separate phases. We have one phase here, we have another phase here, or two windings, two separate windings. This winding is actually displaced equally. We will consider this to be B. We will consider this to be B prime. Again, we are talking about polyphase, a polyphase system. A full rotation is going to be 360 degrees. So therefore we have, it is going to be a two-pole generator. So at about this point here, let's say here, we have 0 degrees. We have up here is going to be 90 degrees. Here we're going to have 180. And here we're going to have 270. It is basically the same concept as the single phase generation. These windings are going to be, supposedly are going to be fixed, and they're going to rotate. They're going to maintain their displacement. So we have at 0 degrees, we have voltage A. So when this part of A, so when A of winding A prime A and B of winding B prime, or B prime B, when they are pointing, when A becomes at N, at the North Pole, it would be at its maximum value. Similar to when B becomes at a North Pole, it will be at its maximum positive value. That is, both maximum positive values. So in this instance, what we have is we have A at 0 degrees, and we have B at 270 degrees at this instance. This corresponds to the instantaneous voltage that is at this instance, which is 0 degrees. As we can see, B is at its maximum negative value, and A is going to be at 0. As A continues to rotate, it will approach 90 degrees, just as the single phase. It's the same single phase, it's just we just added another second phase. As A rotates and becomes in center, at the center line of the North Pole, it will be at its maximum value, that is at 90 degrees, as it corresponds here. And then B will be at 0, because now B has moved, A has moved here, and B has moved at this location. As A continues on, A will decrease in value. It will decrease in value until it becomes at 180 degrees, which would be here. So therefore, instead of A prime being here, it would be A, and A prime would be on the other side at 0 degrees. And in that instance, when A is at 0 degrees, or sorry, when A is at 180 degrees, so A prime is going to be at 0 degrees, and A is going to be at 180 degrees. It has 0 voltage, and B will have its maximum positive value. So basically what that means is that at this instance, currently right now, A has 0 volts. It's producing 0 volts. The instantaneous voltage at A at 0 degrees is 0 volts. The instantaneous voltage at B at 270 volts is going to be minus its maximum value. Basically, it's going to have a minus, a negative sign. Continue on, as we mentioned, as A rotates around and around and around, and it becomes back to 0, and then we restart 0 degrees, we restart our cycle again. With that being said, we can see that the displacement between this system, as of right now, just one thing to remember is that the system is not interconnected. We do not consider this to be an interconnected system. So this is a completely isolated system. Again, the same concept still holds. This is considered, the voltage which is measured here is still considered phase voltage. This voltage here is considered phase voltage. Now, we labeled A and A prime because this is a phase. And these are just legs or lines which are extending from a phase. So therefore we have A and A prime. We have the same methodology and method for B and B prime. So far, this concludes the polyphase system in general. We will go into detail about a more common polyphase system. So far at this point, we have discussed the other polyphase system. Now we will talk about the three-phase system. The three-phase system is the only polyphase system which has the least number of phases that would be considered a symmetrical system. As we see, we have the similar setup as was shown for single phase and the other polyphase system, the two-phase system. We have our pole pieces, we have the individual coils, each phase. As we can see, the individual phases are just displaced amongst each other equally. Following the same logic that we used for the previous voltages in the single phase system and the two-phase system, we see that A corresponds to A. So at the instance of 0 degrees, which is the instance here, A has 0 voltage, C is at its positive value, slightly less than its maximum, and B is at its negative value, slightly less than its negative maximum. So as A continues on spinning in this direction, the direction of the arrow, counterclockwise direction, as it approaches 90 degrees, it increases from 0 up to 90 degrees, or increase from 0 degrees up to 90 degrees, and this will be its maximum. So this is the EM, the E maximum. But we are concerning ourselves, as we mentioned previously, with the instantaneous voltages. This is an example of how instantaneous voltages are also shown and how they also are used for problems in alternating current. So we have here at this instance, A is at its maximum, then it decreases as it spins on. So at 90 degrees, we are here. Continuing on, then we'll be at 80 degrees, 180 degrees, sorry, and that's going to be 0 volts again. As A approaches the 90 degrees, B is also coming in approach. B reaches its maximum. As we can see, it reaches its maximum 120 degrees later from A. C reaches its maximum 120 degrees after B, or 240 degrees after A. That is, A, B, and C B is displaced from A, 120, and C is displaced from A, 240 degrees. As we can see, this corresponds to the chart. We have 0, we have 120 as it's displaced, and then we have another, and then again 240, because we are considering the rotation to be in this direction, which means 240 degrees later, B becomes positive, or maximum positive, and then 120 degrees later, B becomes its maximum positive, and then 240 degrees later, C becomes its maximum positive value. As we can see here, as just noted. Something interesting to make note of is that with this configuration, none of these, that is these phases A, B, and C, they're not coupled together, they're not interconnected. So as of right now, this would be considered a 3-phase, 6-wire system. So we would have 2, 4, and 6. So we would need 6 leads to extend out to this generator. That would be lead A and A prime, lead B and B prime, lead C and C prime, considering when the voltage is in this direction, is in the direction here, we would consider that to be plus. Here would be considered plus, and plus here. And the voltage is in this direction, consider this to be minus, minus, minus. So at this point, instead of having all 6 leads, because usually all 6 leads are not extending out to provide service. We don't have a 6. We do not have a 6-wire. We don't usually have a 6-wire 3-phase system. It's usually 4, maximum 4, or 3 wires sometimes. So in this situation, instead of having, in this instance, 6 different wires, that being A and A prime for phase 1, that is, that we would have, for instance, the equivalent. This would be A, this would be A prime. Then we have B, B prime. Then we have C, C prime. Between, supposing for instance that the voltage across the coil would be 120, and across this one would be 120, and 120 also here. Again, we are referring back to the RMS voltage now, the maximum, or the maximum voltage, which is basically a little less, it's basically the maximum voltage divided by the square root of 2. So referring back to the RMS, and we have 120 volts. So that means that between each of these leads, there's going to be 120, 120. So between line 1 or A, line A of line A and line A prime, we have 120. B and B prime, 120. C and C prime, because these are testing across. This is phase voltage. Now, with this situation, these would feed independent circuits. However, what is done is these can be joined, which make a neutral point. This point would be considered N, or a neutral wire could extend from it also. That is that all of these would be joined together. So therefore, extending from out of the generator, we would have A, B, and C. And then if we desired, and usually it is, there is a neutral which can extend from the common junction that is common to amongst all of the phases. In that case, the system would be considered interconnected. So this is considered a interconnected system. In other terminologies, this is a star or a Y connection. So Y setup. Why is this important? It's important because similar to this system, if we consider this to be plus, this is the other polyphase, minus, plus, minus. Instead of having 4 wires extend from the generator, could have 2 or 3 wires if the common conductor is needed. Therefore, we would have A and B. To summarize thus far, the equivalent for the single phase system in this situation, this winding, its equivalent would be a line to represent it at 0 degrees. As far as this polyphase system is concerned, the equivalent is also a single phase. This line we call A and A prime. As we mentioned, it is the equivalence of this. And B and B prime. As we know, we were joined at this location. So in this situation, we have a 90-degree displacement. That is, B lags A by 90 degrees. In the single phase system, in the single phase system we have 0 degrees, as we mentioned. The equivalent for the sine wave would be E M, say E maximum, is sine theta. So that is this is a representation of the sine wave, which is basically, as we represented, this sine wave, its equation is Em sine theta. Similar to this system, we did represent that system previously. The equivalent of that system, A, still we have A equals Em sine theta, B equals Em sine theta minus 90 degrees to represent lag, or could also be written as Em minus pi over 2. The equation for A, which is here, is going to be Em sine theta. For this system, which is a 3-phase, we have A will equal again Em sine theta, which is E maximum sine theta, B EM sine theta minus, if you look back, because B lags A, positive voltage will lag A. So we have minus 120 degrees. And C, same equation, be representing this value here, EM sine minus 240 degrees, because we see that C lags A at 240 degrees. Or we could express this as EM is equivalent to EM sine theta minus 2/3 pi. C equivalent to theta minus 4/3 pi. So with that being said, we can see that with the equations that we have here, the equations that we have here so far will represent the sine waves. The basis is the sine wave of voltage up to the sine wave of voltage for the single and sine wave for the voltage for two-phase and for three-phase system. We spoke in the past that we mentioned a few of the voltages, and I wanted to add that the RMS voltage, going back to the maximum voltage equals the square root of 2, the RMS voltage, square root of 2 times the E RMS. That follows that the RMS voltage is the maximum voltage divided by square root of 2. So in this situation, if, for example, if our voltage, the RMS value, the mean value is 120 volts, the RMS, the maximum value, so if our E equals 120, the EM is going to be 120 times square root of 2, which is about 170 volts. So that basically means that the E maximum will exceed, it'll be about 70% or so more than the RMS. The average voltage is about 63.7 some percent. So a little bit less than the RMS voltage. In conclusion, we have covered so far the types of voltages, and overall the conclusion thus far is that we have that voltage is basically an expression of EMF in volts, and that for the majority of work which is performed, the voltage which is usually sought is the RMS voltage. God willing, we have concluded this subject up to this point.